Hey, what's up guys? It's Nicola from Calcunic, and today we're going to be going over a few harder examples involving trigonometric identities. Let's get right into it. So in this video, we'll be covering three slightly harder trigonometric identity examples, and throughout the video, I'll try to speak my mind as much as possible, so hopefully you guys could understand my thought process and how I come to conclusions during the solution, so that you too could successfully solve these kinds of problems in the future. I would definitely recommend pausing throughout the video and trying to see what you think the next step to the solution should be. I've just found that, in my experience at least, that when I try to solve examples before watching or reading the solutions, I usually gain a much better and deeper understanding of the concept. So without further ado, let's just jump right into it. In our first question, we're asked to prove that secant A plus cosecant A over tangent of A plus cotangent of A is equal to sine A plus cosine A. And we see that in this question we have one side that's pretty simple, the right-hand side, and we have that the left-hand side is slightly more complicated. And usually when we're faced with problems like this, the best way to solve them is to start with the complicated side, in this case the left-hand side, express everything in terms of sine and cosine, because sine and cosine is easy to work with, and then simplify it, and hopefully we can get to something that resembles the right-hand side. So let's see what we have to do then. We have that the left-hand side is equal to, secant A is equal to 1 over cosine A, and that's going to be plus cosecant A, and cosecant is 1 over sine A, and that's going to be all over tangent A. Tangent is sine over cosine, and that's plus cotangent, and cotangent is cosine over sine. All right, great. So we reduced everything into terms of just sine and cosine. And because we have a few fractions here, let's try to find common denominators and group them together. So for the first one, we have cosine and sine. So our common denominator is going to be sine A times cosine A. And so for the numerators, in our first expression, we had to multiply by sine A to get the common denominator. And for the second one, we multiplied by cosine A. So our numerator is going to be sine A plus cosine A. And for the bottom of this fraction, again, we have the same denominator, sine A times cosine A. So we're going to have sine A cosine A here. And in the numerator for this lower fraction, again, we had to multiply the first expression by sine A and the second one by cosine A to get the common denominator. So our numerator is going to be sine A times sine A, or sine squared A, and then plus cosine times cosine, cosine squared A. All right, perfect. So now we're here. Let's see what we could do next. We can notice that we have both sine A cosine A and sine A cosine A twice, so we could actually reduce that term as it cancels out. And what we're left with is going to be sine A cosine A, and that's going to be all over sine squared A plus cosine squared A. Well, that's good. The denominator here, sine squared A plus cosine squared A, that's just the Pythagorean identity. And we know this is equal to 1. So we could just cancel this term out because anything divided by 1 is just itself. And so we have our final answer, sine A plus cosine A. And this is equal to the right-hand side of the initial equation as desired. So to recap what we did here, first we started with the more complicated expression over here, and we expressed all the terms as just cosines and sines. We then found common denominators and grouped together, and after reducing we were able to find the final answer, sine A plus cosine A, which was just the right-hand side. In this question we're asked to prove that sine A times 1 plus tan A plus cosine A times 1 plus cotan A is equal to secant A plus cosecant A. Like the previous question, we have a more complicated side to the equality. So we're going to start there and try to evaluate everything in terms of sine and cosine. So we say that the left-hand side is equal to, we have sine A times 1 plus tan A, which is equal to sine A over cosine A, and then plus cosine A, and that's going to be times 1 plus cotan A, and cotan is cosine over sine. All right, so now let's multiply this out. We're going to multiply sine with 1 and then sine over here, and cosine with 1 again, and cosine with this term over here. So what we're left with, we have sine times 1, so just is equal to sine A, plus sine A times sine A over cosine A. So we have sine squared A over cosine A. And then over here we have cosine A times 1, so that's just cosine A, plus cosine A times cosine A over sine A. We have cosine squared A over sine A. All right, so let's look at these two terms right here. For the first one, we have sine squared A over cosine A. And unfortunately, we can't do anything to reduce that right now. But it'd be really nice if we could somehow express this sine squared A term in terms of cosine. And actually, we can do this using the Pythagorean identity that says that sine squared of some angle A plus cosine squared the same angle A is equal to 1. And so what we could do is move the cosine to the right-hand side. And that's going to leave us with sine squared A is equal to 1 minus cosine squared A. And similarly over here, we have cosine squared A over sine A. We want to express the cosine squared somehow in terms of just sine. And for this, we're going to move the sine to the right-hand side. As we did with the cosine in the previous, we're going to get that cosine squared A is equal to 1 minus sine squared A. Now we make the substitutions into the equation to simplify it. So from before, we have sine A, and then plus sine squared over cosine. Sine squared is 1 minus cosine squared A, as just proven, over cosine A, and then plus cosine A. And then we have plus 1 minus sine squared for cosine over sine A. All right, now let's do some reducing. So again, we have just sine A, but we have plus, we have 1 over cosine A, and 1 over cosine A, that's the definition of secant. So we say secant A, and then we have minus cosine squared A over cosine A. That's equal to minus cosine A because these squares cancel out. Then we have plus cosine A, and plus we have 1 over sine A, and 1 over sine A, that's cosecant A. And then we have minus sine squared A over sine A, that's equal to minus sine A. And we have this long expression now. Let's do some reducing. So sine A reduces with negative sine A, minus cosine A with cosine A, and all we're left with is just secant A plus cosecant A, which is exactly equal to the right-hand side, the desired solution. So in this question, we're asked to find sine of 2x if cosine of 3/2 cosine x is equal to sine of 3/2 sine x, where x is in between 0 and pi over 2. And this question was featured in the Euclid Math Contest of 2019. I believe it was question 8B, and I actually did this contest, and I remember really enjoying doing this problem and thought it'd be nice to share it in this video. Keep in mind that this problem is likely harder than anything you'll see in a school setting or in a school test, but nonetheless, there's still a lot we can learn from it, and it really isn't that hard to actually understand once you see the trick to doing it. So the first thing when I saw this problem was to look at sine of 2x right here. And I wondered why sine 2x? Well, we know by the double angle formula that sine of 2x is equal to 2 times sine x times cosine x. So I knew that when I was going to solve this problem, I would want to look for this term here, 2 sine x times cosine x, because once we see that, we could immediately change it to sine of 2x. Now we go on to the actual equation. Cosine of 3/2 cosine x is equal to sine of 3/2 sine x. Well, this is tricky. There is no formula to help us with cosines of cosines or sines of sines, so we have to manipulate this equation somehow to resemble something that we actually know how to solve. When I saw cosine of something is equal to sine of something, it made me think of the complementary angle formula. this formula basically says that if we have two angles A and B, and we're told that cosine of A is equal to cosine of B, and also 0 is less than or equal to angles A and B, which is less than also pi over 2, which is just 90 degrees if you didn't know, then in that case, we could say that A plus B sum up to 90 degrees, or pi over 2. So we have in our question cosine of 3/2 cosine x, which would be our A term in this case, and sine of 3/2 sine x, our B term in this case. However, we need to first prove that angles A and B are in between 0 and pi over 2 to make sure that we could invoke this formula that A plus B is equal to pi over 2. Well, we have cosine and sine, and we know that 0 is strictly less than x, which is less than pi over 2. So we know the angle x lies in the first quadrant. And in the first quadrant, cosine and sine are both positive. So we could say that 0 is strictly less than sine x and cosine x. And it's also strictly less than 1 because sine and cosine don't output values greater than 1. We have 3/2 here, so let's multiply everything by 3/2 to resemble it. So 0 times 3/2, that's just 0. 0 is less than 3/2 sine x, 3/2 sine x. And it's also going to be less than 3/2 cosine x. And this is all less than 1 times 3/2, or just 3/2. All right, so we have our first base case. We have 0 is less than, but now we need to show that this is less than pi over 2. Well, is 3/2 less than pi over 2? We know that 3 is less than pi, right? Pi is 3.14 and 3 is just 3, so 3 is less than pi. Then it must follow that pi over 2 is strictly greater than 3/2, and in turn 3/2 sine x and 3/2 cosine x. And so therefore we could implement the complementary angle formula. We can say that A plus B is equal to pi over 2. Or in terms of this question, A, which is 3/2 cosine x, plus B, which is 3/2 sine x, is equal to pi over 2. All right, great. And this is really the hardest part of this problem, recognizing that we have complementary angles and transforming this seemingly impossible to solve equation into something that seems a bit more bearable. However, we're not just done yet. Let's move on. So let's factor out a term of 3/2. Just to make it a bit more simple, we have 3/2 times cosine x plus sine x is equal to pi over 2. Now we're going to divide both sides by 3/2, or multiply by 2/3, the reciprocal, and we're left with cosine x plus sine x is equal to pi over 2 divided by 3 over 2. That's just pi over 3. And now we're left with this. We have cosine x plus sine x is pi thirds. And we're looking for sine of 2x, which is known to be 2 times sine x cosine x. So how can we take this expression here and transform it to somehow resemble 2 times sine x times cosine x? So there's no clear-cut formula to go from sine x plus cosine x, but there is a cool trick that we could use. What we're going to do is we're going to square both sides of this equation. And basically when we square it, we're going to have a term of 2 times sine x cosine x in the middle of the square over here. Let's see what it looks like. So cosine x plus sine x squared is going to be cosine squared x, and then plus 2 times sine x cosine x plus sine squared x. And that's just equal to pi squared over 9. And look at what we got here. We have 2 times sine x cosine x, which is exactly sine 2x. And even better, we have cosine squared x plus sine squared x. Well, from before, that's the Pythagorean identity, and we know that this sum is just equal to 1, so we could write that now. Moving on, we have 1 plus 2 sine x cosine x, which is just sine of 2x as discussed, and that's equal to pi squared over 9. And just by rearranging, we get sine of 2x is equal to pi squared over 9 minus 1, the final answer. So to recap our process in solving this, the first big step was to look at this equation here and transform it into something that we could work with. And we did this by recognizing we could use the complementary angle rule to transform it into this expression here. The second big step was to see that we had cosine x plus sine x is equal to pi thirds, and that we could get sine of 2x just by squaring both sides of the equation, which would give us 2 sine x cosine x, and then just the sum of sine squared and cosine squared, which is just 1. Now, once you actually see the solution, you see that this problem isn't actually that hard, right? The solution could fit on one entire slide. But when you're actually in a test-like situation, it's a lot harder to come up with these situations on your own. And my advice to you is just to practice. The more you practice, the more examples you see, and the more tricks you can learn, like the squaring trick here, or the complementary angle trick right here. And the more tricks you're familiar with, the more examples you've seen, the more natural this process will come to you. And before you know it, you'll be able to solve these problems like it's nothing.
Alright guys, thank you so much for watching. If you had any questions about the video or just other video suggestions, drop them down in the comments below. I do try to get to all of them. And if you liked the video, leave a thumbs up. And if you loved it, subscribe. That's all for me. Till next time.